1. So it's in here, right? So I'm going to put a little check mark. It's in the domain. This is in the domain. That means I need to check it. What if that wound up, what if that instead was the point like 5, 2? I wouldn't check it, right? I would just chunk it. Question?
No, I have one, but
You're good? Okay. All right, so that's the first step. Now, the second step, which is the new part, which is what today is about, is trying to figure out what's happening around the boundary. Y'all ready for this? Step 2, find max, min on I always have trouble spelling boundary. I don't know why. A-R-Y? Boundary? Boundary, like that? I knew that much. I knew it was a Y at the end. Seriously, my brain gave up on the English language a long time ago. I just gave up. Shut down. All right, so you know how when I was showing you this image, what I did is I broke the triangle down to 3 different pieces, and I just looked along each one. I said, hey, along this edge, we're a line. Along this edge, we look like a parabola. Along this edge, we look like a line. It's exactly what we're going to do here. We've got to break this boundary down into pieces. So let's go ahead and label it now. Let's call this first. And we could pick any. There's not like always do this. You know, I'm going to say from here to here is the first thing I'm going to look at. I'm going to call that L1. All right? So let's talk about L1, then we'll get to L2 and L3. On L1, let's discuss what's happening. On L1. So everything I talk about from here on out is just in reference to L1. Tell me about the points that live on L1. Tell me about all these points. What do they all have in common? Y is 0, right? Y is 0. So they all look like this. It's some x coordinate, and then your y coordinate is 0. Agreed? All points along that line look like that. And there is some little slight restriction, though. X can't be anything, right? X has to be between 1 and 5, closed interval. Or I'll say with x being between 1 and 5. Closed interval. Do you see how this is starting to already look like a Cal 1 problem? I have a closed interval with just x. You'll see that? Now, let's go ahead and plug these points into our function and see what we get. So what would we get if we plugged in f of x, and instead of y, what can I say about y? It's 0. What do I get if I plug in f of x 0 into that? So replace all your x's with x's, all your y's with 0. 3 minus x. That's what you would get, right? Now you're really in a Cal 1 problem, because what you can do is you can imagine this is some function of x right there. And you want to find its maximum and minimum value on that closed interval. Understand? So what did we do in Cal 1 when we had a function of a single variable on a closed interval and we wanted to find the max min? We take the derivative of this and set it equal to 0. And then we take the endpoints and we take the answer to that derivative being to 0 and compare them, don't we? That's what I'm going to do now. I'm going to take the derivative of this. Now I'm going to indent this a little bit on purpose, because this is like I'm still working with in here. I'm just taking a quick derivative of this, and we're getting what for that derivative? -1. And I'm asking myself, when is that 0? Never. Well, that makes sense. Remember we said when we plugged that line in, it gave us a line? It looked like it did. Well, the derivative is the slope of that line, and the slope we're saying is -1. Okay. So we have no critical points, do we? We have no critical numbers from this. So I'll just put here, there's no critical numbers from this particular incident of moving along L1. So therefore, all I have to do is plug in the two endpoints. So can we do that? Plug in the two endpoints? So what would the first endpoint be? Plugging in 1 for x. So I'm really looking at what's f of 1, 0, which is right in here. 2. Okay, what's the other one? F of 5, 0, which would be -2. Got it? Okay. Save those. We'll come back to those in a minute. All right? All we've done is we've moved along L1. We found that we do actually have a highest value along L1. It's at 2, right? The highest value is 2. The lowest value is -1. Let's just go back and take a quick look at the picture and see if our picture corresponds to this. Try and squeeze it in right there. We were on the blue. Oh, come here. Whoa. Okay. Turn. Can you all tell this is L1 right here? And when we plugged in 1, 0, which would have been this point, it spit out 2. And when we plugged in 5, 0, it spit out -2. All right? And nothing in the middle because this right here, the derivative was -1, right? All make sense? Okay, let's continue to move around the closed bounded region. So let's go L2. Let's let L2 be, well, you want to go with the hypotenuse of this now, or do you want to go the easier one, which is this? You want to do the easier one first? Okay, let's do this one. L2. This green really does not come out good on camera, but I think you can see it enough. All right, so L2. So we set up a whole new piece of information here. So tell me about the points that live on L2. Tell me about those guys. X is always 1, right? And the y coordinate, it varies, doesn't it? It varies from 0 to 4. So all points on L2 look like this. 1 for the x coordinate and y for the y coordinate, where y is always between 0 and 4. So now you're going to plug all those points into the original function. Replace x with 1, y with y. So what's f of 1y? Up there. Yeah. It's 3 plus 1 times y minus 1 minus 2y. So what is it? 2 minus y. There we go. It's 2 minus y. So any questions? If we follow the same procedure now, what we would need to do is find the critical numbers of this, acting as if this now is a brand new function of a single variable. Now, the fact that it's y, not x, let's not let that freak us out. It's the same thing that we had when we had, x in here. We're going to take the derivative of this with respect to y, and this is going to be our closed interval. So what is the derivative of this with respect to y? -1, and that's not ever 0, right? So I don't have any critical numbers there? So all I need to do now is evaluate this function at the two endpoints, 0 and 4. So I need to go f1 of what? f1, 0, and then f1, 4. Understand? And I've had students in the past ask me, do you plug the 1, 0 up into this, or do you plug the 1, 0 into this? What's the answer? This is easier. You're going to get the same result, okay, either way, but this one is less work. We already know what happens when you plug in 1 for x. That's what happens when you plug in 1 for x. We just want to know what happens when you change the y, which is this. So what happens when I plug in 0? 2. And then when I plug in 4, -2. Save these. We'll come back to those later. Do you see that we actually repeated ourselves here? We already had found 1, 0, hadn't we? We had done that in the last problem. That's because our two lines, they overlap each other, don't they? They overlap each other? Okay. All right, now we've saved the hardest one for last. Let's move along L3. Do y'all have any questions? So far, it's straightforward? No voodoo magic here? We've been pretty lucky with L1 and L2 because on L1 the y coordinate was fixed. Yes? Oh yeah. On L1 the y coordinate was fixed. On L2 the x coordinate was fixed. Got it. All right. How about on L3? Are either one of the coordinates fixed? As you move along this, your x and y coordinates change, don't they? But if they live on the line, there is a relationship. And that's what we need to determine, is what's the relationship between x and y here. So how do you think we're going to find the relationship? Find the equation of the line, right? That's a line. Find the equation of a line. Well, what do I know so far? I have one point here, which is 1, 4, and I have another point over here, which is 5, 0, and someone in college algebra told me once that to find the slope between two lines, it's like y2 minus y1 over x2 minus x1, right? Something like that. So what's the slope of this line, L3? I'll do the work right here. What's the slope of that line? -1? Is it? It is. It's -1. But we need the equation of the line, so how would you get the equation? You could use this formula, remember this one? Or there's another one, y equals mx plus b. But if you do that one, you have to know the y-intercept, which you don't. Well, you kind of do, but you could cheat by just knowing you go over 1, up 1, but that's fine. I'm just trying to give you a general idea. If this line wasn't so pretty, because it is pretty, it's slope -1, but if we didn't have that, then how would we do it? I would probably scrap this. I'd go to this right here. So just pick one of those points as your x1, y1. You have y minus, let's pick this one. This is an easier line, easier piece to work with, right? So that's going to be y minus what? 0 equals m, which we said our slope was -1. X minus 5. And just clean that up, and we have y is equal to -x plus 5. Got it? So if we live on L3, right, if you are a point on L3, here's what I can tell you about that point. It has some x coordinate, right? And the y coordinate is always -x plus 5. That's the relationship between those 2 points. Whatever this is the y has to be that. Yeah? Questions?
Where did you get the x?
This? Just I'm picking an arbitrary x. If I come out here and I say, hey, okay, pick an x, that takes me to here. Now what's the y coordinate going to be? To live on the line, the y coordinate has to follow the equation of the line. So the x was arbitrary. Okay, so now what we'll do is, just like we did before, all the points on this line L3 look like this, x, -x plus 5. And we do have a restriction on x, right? What's the restriction on the x that I plug in to be on this line. Smallest x I can be is 1. The biggest I can be is 5. So I still have this restriction. Plug this into that. You get what's f of x comma negative x plus 5. This is 3 plus x times the y, but the y is negative x plus 5. And then minus x, and then minus 2 times negative x plus 5. You see, that's just the original function with all the y's replaced with negative x plus 5. Anybody have any idea what type of function this is going to be when you put it all together? It's going to be a parabola, right? Because I showed you the picture. When you plug that line in, we got this black parabola, didn't we? This better turn out to be a parabola. It's going to. It's, let's see, 3 minus x squared plus 5x minus x plus 2x minus 10. Clean it up. Negative x squared. Negative x squared. How many x's do we have there? 6. 6 x's. Constant. Minus 7. Boom. There it is. So I mean, this is really cool, I think. I don't know. I think a lot of things in math are cool, so I don't know how that translates to you. But what we know right now is when you plug this line in and you throw that into this function and you look above, like if you're standing there on this line, you looked up, it would be a parabola. And it would be opening down because you're negative in the front, it's going to open down. And so what we want to know is what's the maximum and minimum values of this on this closed interval. So now the derivative is going to matter, right? We're going to take the derivative of that. So what would the derivative of this x comma negative x plus 5 be? Negative 2x plus 6, right? And then from there, you set that to 0. F prime equals 0. Well, that's going to be negative 2x plus 6 equals 0. So x is 3, right? X is 3. So we actually have a critical number this time, don't we? If x is 3, can you tell me what point that is over here? Come back to this. If x is 3, where are you? 3, 2, right? 3, 2. Plugging in 3 for those. So this implies that 3, 2 is a critical point. Understand where the 3, 2 came from? Yeah? So what I do now is that's the only critical point I have. What I need to do now is I need to look at this function at this point and at what? X is 1 and x is 5. See, I haven't done that part yet. So I'm going to write those out. So I'm going to look at what happens when I replace the x with 1. So put 1 right here. We get 1, 4, right? Replace the x with 5. I get 5, 0. And then replace the x with 3. I already know what happens. I get 3, 2, right? So I'm taking the two endpoints, and I'm taking the critical point, and I'm going to plug all those into the original function. And let's see what we get. We already know the first two, don't we? Because we already did those, didn't we? Didn't we do that point already? Didn't we do that point when we did L1, L2? What were those? 1, 4 was negative 2, and then 5, 0 was 2? Oh, it was the other way around? It's 2 here? Yeah, 2 and negative 2. Okay. And then what about F3, 2? We have not done that yet, right? We've never plugged 3 and 2 in there. So let's go ahead and do that. Plug 3, 2 up there. We could actually plug, no, that's the derivative. We could plug it into the parabola.